we have a nested list of integers, okay? Each element is either an integer or a list whose elements may also be integers or other integer lists. Our task is to implement an iterator to flatten the nested list. Sweet. So our deliverable, what we have to implement is a nested iterator class. So a class definition called nested iterator. And it has these functions: a constructor that initializes the iterator with the nested list, a next method that returns the next integer in the nested list, and has next that returns true if there's anything left in the nested list. Otherwise, it returns false. Okay. And so as an example, this is something similar to what we will be dealing with. You can see that we have some integers and then some are nested within like so. And so we store it inside like this, right? You can see it's an array instead of just an integer. But whenever we hit next, has next, it's going to say true because there's something here, something left here. And then when we call next, it's going to pop it, take it out of there. And then when we call has next, you can see that it transformed this array, flattened this array into integers, and then it says true, and then next it takes things out one by one. So they want us to make a class that does that. And what does the solution look like? Well, we're going to have a class with the 3 methods, and that's a constructor, the next and the has next. Now in JavaScript land, this solution is a bit interesting because they use the prototypical manipulating a prototype to get to simulate class behavior, because all JavaScript doesn't have classes in the original sense of things. So I decided to refactor the code into TypeScript and use JavaScript classes, basically, which is a newer feature, relatively newer feature compared to JavaScript itself. And so we're going to use a stack to solve this problem, because that's the series we're following right now, like, is stack-based problems. And now it's going to store the integer and list of integers on the iterator object. So in every instance of our class, it's going to store the integer and the list of integers on itself. And we'll push all the nested list data into the stack in reverse order in the constructor. Okay, and I'll just go right into the solution. So we have this class right here, and you can see in the constructor we're passing in a nested list, and we are reversing it when we put it and spreading it into this stack property for our class. Okay, and this nested integer class is something that is given to us. If you check LeetCode and if you look at Educative, they provide this implementation for us, and what it does is it can hold either a normal integer or a list of integers, right, within itself. So we are not tasked with implementing this, but they do give it to us, and they tell us all the methods every instance exposes. Okay, so don't bother yourself about this. What matters is this constructor, one of our deliverables. So we've done one part of the problem already just by doing this, which is nice. And then, so it's pushed in the reverse order because the iterator is implemented with a stack, okay? And in order to process the nested list correctly, they need to be accessed in the order they appear in the original nested list. So that's why we put them in reverse order, because the last thing that goes in is the first thing that comes out. So if you reverse the list, the top of the stack, when you pop something, is going to correspond to the beginning of the list because we've reversed it. Okay, and it's something you can intuit by just like maybe going through it a couple of times or looking at a diagram I just shared right from here from the beginning. So you see that if this were a stack, the thing on top is the thing in the beginning, and so when you're putting things into the stack, you want to start from the end so that what's in the beginning becomes what's on top. Okay, that's basically what I'm saying. Now for the has next function, this one is a bit of a doozy, so pay attention. But we're almost there. We're 1/3 of the way there. It performs a set of push and pop operations on the stack in the form of a loop. Okay, it checks if the top element is an integer, so if it's a flat value or if it's a nested or the list of integers. Is that or a list of a list of a list of integers, like a what they call those Russian dolls, or an onion, right? So it checks if the top element is like a base value, an atom, if you will, is an integer, and if so, it returns true. Otherwise, if it's not, if it's something nested, if it's a list of integers or something nested, a nested list of integers where it's nested to an arbitrary length, then it pops from the stack and pushes each element of the list in the stack in reverse order, again, in reverse order, so that what's in the beginning corresponds to what's on top. And this way, the list at the top of the stack is converted to individual integers whenever the hasNext function is called. So that conversion happens when our hasNext is called. And if the stack is empty, it's going to return false. And now is a good time to look at what happens here. So this is the method that we just discussed. And it's going to use this while loop just in case there's any nesting. Okay, so it checks if is there anything here, right? If this is false, then it's just gonna say, yeah, there's nothing to return. But in this case, there's something. So we're going to get the thing on top. And then we're going to check if it's an integer. Now, this is integer method is implemented on our nested integer class that we're provided with. Okay, so you don't have to implement this yourself. But it tells us if it's an atomic value or not. And if it's atomic, if it's just an integer, not a list of integers, then we just return true and we're done. We're done here. This while loop breaks, hasNext returns true, safely. Now, if that isn't the case, if there's a list in there, we have another getList method that's again implemented on the class that is provided to us, and that list we want to flatten. So how do we flatten that list? We get the length, how long the list is, we loop from the back again, right? This is another like interesting way to loop through the back, right? You notice here we use the spread operator and the reverse function that JavaScript gives you, like on every array. But in this case, we're using this while loop, right? We're using I starts from the end. So if our I is greater than 0, we're going to be decrementing I till it hits 0. We push things onto our stack once again, and that helps us flatten things out. So that's a flattening operation. And that's all there is to it, really. And eventually, with time, regardless of the level of nesting, we're going to have this breaking condition here. So it's similar to like a terminating condition when you're dealing with recursion. And if you've been following, right, we've covered some recursion a couple of videos back, right, a couple of steps back under some dynamic programming problems and some subset problems. We did a couple of recursion related problems there. So this is a similar pattern. Okay, next we're going to deal with our next function, and it first calls hasNext to check if there's an integer on the stack. Okay, so we check so we don't have like a stack underflow, right? So it checks, is there something? And if there's something, if it's true, it returns true, and we pop that thing from the stack and return the popped value. Okay, and they give us this diagram that's similar to the one we just saw when I was stating the problem in the first place. But let's just look at the code real quick. So it's very short. So if there's something next, return that thing, right? Just pop it, then get the integer. And then remember that this is going to flatten anything we have. So then this is always going to be like an atom, right? It's always going to help us such that we can get the integer instead of getting a list like we did here in hasNext. And otherwise, right, if there's nothing, just say no. There's nothing more to say. There's nothing to return. So return null. And that's it. That's all there is. That's all that's expected of us in this problem. So that is the TypeScript solution. That's what it looks like. For the JavaScript solution, I guess I can show you real quick. So you can see they use patching, right? They're patching the prototype for this function. This is the constructor essentially in JavaScript land. And this is how we implement hasNext, right? We patch the prototype, but the same function definition really at the end of the day. Same with next. Okay, so that's Educative's way. They showed you the JavaScript one, but I'm showing you the TypeScript one because it's similar to other languages like Java, C++, and even Python. So yeah, thank you for watching. Like, comment, subscribe, upvote, share, tell a friend, and let's grow this channel together. Before I go, let's talk about time complexity. So it grows linearly, right, with the total amount of lists and nested lists that we provide. So they give this explanation. So assuming n is the number of elements, L is the number of nested lists, and D is the maximum nesting depth, so the maximum number of lists inside each other, our constructor pushes everything from the nested list onto the stack. It doesn't convert anything. So the total time complexity will be the size of that list. Therefore, the time complexity will be the number of individual things plus the number of nested things, right? We separated two. And then hasNext. So this function will be called several times. Every single time we call next, hasNext gets called. During all the calls, it will iterate over all the lists exactly once in the while loop, that while loop that we showed earlier, and process every integer exactly once. Thus, a total of O of n plus L effort is spent. So the same n plus L, where n is the number of atoms, L is the number of molecules. You can think of it like that, or lists. And now the iterator will be progressed, like it will make progress for every integer in the nested list, okay? And there'll be a total of O of n calls, okay? Accordingly, the runtime for one call to hasNext is n plus L divided by n, which is L over n, which I find uber confusing. Yeah, like with all things recursion, the time complexity is something you might want to internalize. So if you have a better explanation, I can make this clearer. Just let me know in the comments. Thank you so much. Otherwise, the next will call, it calls the hasNext every time. And so the complexity will be the same as hasNext, which is O of L divided by n. But this is very easy to internalize, right, for the space complexity. So this one is n, the number of individual things plus the number of lists of things. And in the worst case, where the outermost list contains n integers or n L empty sublists, it will cost that, right? That's the worst case. And now there are other cases that happen when the nesting is very deep. But again, we're dealing with nesting and recursion. So like time complexity tends to be something more complicated than we're usually concerned with. But if you just say n plus L, right, I think whoever is evaluating you should be satisfied. That being said, feel free to give like a point to solid resources in the comments or explanations. And thank you. Like, comment, subscribe, upvote, share with a friend. I'll see you next time. Cheers.